Hi everyone. As introduced before, my name is Dominik. I work as a Developer Evangelist in Berlin for a company called Twilio. For those of you who don't know what Twilio is a cloud communications platform that allows US developers to easily build different means of communication such as voice, video, messaging into applications using just a simple set of REST APIs and client-side SDKs. But today the topic of my talk is going to be TypeScript. I'm going to walk with you a bit about through why you might want to use TypeScript, what TypeScript is actually about, and how you can get started even with existing projects to start using TypeScript. Quick warning, most of the talk will be live coding, so I will have the slides available, but they won't be much of use, so pay attention, especially when there's code on the screen. So let's talk about TypeScript. So what is TypeScript? TypeScript is a project that started a couple of years ago, around 2012, by Microsoft as an open source project that defines itself as a superset of JavaScript. So classic diagram time. So if that's all the features that are supported with JavaScript up to ES5, and then that's everything that came with ES 20, 15, 16, and now 17, then this is pretty much what represents TypeScript. So TypeScript is basically everything that is valid JavaScript plus a bit more. So before we can talk more about TypeScript, I figure we're gonna kind of brush up our understanding of JavaScript for a couple of things that actually helps us to write better in TypeScript. So for that, I'm gonna jump into the Node repo. There we go. So I suppose we're at a front-end conference. I think you all know your fair share of JavaScript. So you all know that you can either use var, let, or const to define a variable. So let's define something like foo. But contrary to statically typed languages, we don't really specify like what's the type of a language of the variable, right? And this is typically where in dynamically typed languages people kind of completely forget about types. So I would like to kind of just give a quick refresher of what are things that are useful to know about types that do exist in JavaScript, because JavaScript uses types. So first of all, we have the Typeof Operator, which lets us check what the type of something is. This is not a function, so calling it like this is kind of useless because it's actually this. So aside of number, which is the only type of number we have, there's no difference between floating point or integers. We obviously have Boolean, we have functions, we have strings, we have objects, and this is where the sanity of TypeScript stops and everything else kind of becomes weird. So arrays are objects. There is a way to check though if something is an array, so because obviously that's something common, we can check using array as array. Another way to do this would be to check if it's an instance of, and this is another one that is useful because if we, for example, have a date, and we want to check if that's actually a date, we can use the instance of operator. The other thing that we need to know, aside of being able to check types, is that JavaScript likes to mess with types. So if we, for example, add two arrays, that doesn't merge the two arrays, it actually calls toString on both of them to kind of match them and ends up in an empty string. Similarly, if we would add to an array an object, that just casts the object to using the toString method, and the result is object. Unfortunately, this, again, is where the sanity of JavaScript stops. Similarly, if we would add two objects, that again casts everything to strings. Interesting enough, this one, the 0, in some browsers that's not a number, so don't even rely on that, that actually makes sense. But basically the bottom line here is that we can't really rely on JavaScript doing necessarily the right thing that we believe it does, because it might just do, like it will try to do something with the types to match them and do something reasonable, but we can't really rely on that, and therefore, for example, if you are in your application and you expect a certain type to be given to a function, that might not be the case because JavaScript might have changed that at some point during the execution. All right, so back to the presentation. So yeah, we've seen types in JavaScript exist, but they're weird. And in big projects, this can quickly turn into a mess. You don't know what kind of type the function that is like 5 files away expects. And if it's a really big code base, it's hard to keep track of if something changed, where did it break? And since we don't have a compile time in JavaScript, typically you encounter these things either if you're lucky during your unit test, if you're semi-lucky during manual testing, and if you're completely unlucky, the code will implode in front of your user's face. And that's not a great experience. So what does TypeScript offer to kind of solve this problem? TypeScript effectively is 2 things. So the first one is it's a compiler that converts TypeScript, the language, into JavaScript. You can just simply install it via npm, either globally because it's a command line tool, or locally. I always recommend doing it locally because this way you're able to have different versions of TypeScript for different projects without kind of binding yourself to either having to use a really old version because there's this one project that you definitely can't update, or the other way around where you have to go kind of around and every time like update every project because you try to use the latest one for a certain project. And then it's TypeScript, the language, which basically extends JavaScript with a set of type annotations that allow us to give more information about the source code that we have, and then let the compiler type check these during compile time. It also gives us a better development experience thanks to the TypeScript language server, which basically allows you to deeply understand the JavaScript source code and give you better autocomplete and other things that you will see throughout. This is directly built into Visual Studio and Visual Studio Code. So if you've been writing JavaScript before in Visual Studio Code, for example, you got already a couple of these benefits. But there are also extensions available for most of the common editors. With that, it's the end of my slideshow, and we're going to jump into some coding. All right, so I have an empty project here, sort of empty. The only thing that I did is I already installed TypeScript, so I'm using 2.5, which is the current stable version if you would run npm install. And inside here, we will see that there are 2 binaries here. One is the TSC, which is the TypeScript compiler, and then the other one is TS server, which is the TypeScript language server that is being used to analyze the code and understand the code and give us better autocomplete. I also made sure to, in this case, point VS Code to actually use the TypeScript language server that we're using here. All right. So I said that we will that every valid JavaScript is valid TypeScript. So we can start with saying something basic like hello frontend connect. And since there's no JavaScript, no TypeScript involved here yet, we can just execute it, and that works. So to highlight a couple of the benefits of JavaScript, we're going to write a very basic concat function. And don't roast me here, this is going to be the most naive concat function you've ever seen. But it highlights a couple of good examples of things that TypeScript can do for you. So we'll basically just iterate over input B and then push every element that it is in their input into input A and then return input A. And then we can call this. And if we execute this, you'll see down here 1, 2, 3, 4, everything seemed to work. Now this is an unrealistic example, right? Like, why would I write a function to merge 2 arrays that like are literally next to each other? I could have just merged them directly. It's more likely that you have something like, hey, we're going to pass in 2 variables A and B, and they're determined somewhere in your source code by a function that probably you didn't even write. And then they're called later. So this code still works, it's still basic JavaScript. And now one of your colleagues comes and is like, oh, I have this great idea, I'm going to start returning instead a comma-separated list. And the reason might be because you're fetching this from a network request, and they're like, oh, it's way easier for me to, like, instead of converting that into an array, I'm just gonna like pass it as a comma-separated list. And interestingly enough, if we execute this code, you'll see the code still works, and the reason is that strings fulfill the two criteria that are necessary for our code to work if, given input B. One is that it has a length property, which strings do have, and then the other thing is that it's accessible by index, which it does as well. So basically we're just iterating over every character and push them into the array, which is not necessarily what we want, but the code doesn't break, so it might actually be something that one of your colleagues loves because it's like this behavior that is really neat for them. So far so good, but what if we swap these two around and actually call the string as the first one? So if I execute this now, boom, the code implodes because strings don't have a push method. So while it fulfilled sort of the criteria of input B, it doesn't fulfill the criteria of input A. So how can we use now Typescript to kind of make this more bulletproof and save us from having this code implode in front of our face? This is where the type annotations come in, because what we really want when we wrote this code is that we expected input A and input B to be arrays, right? We don't really care what sort of arrays, but they have to be arrays. So what we can do is we can just say that, like, hey, input A and input B are any array, and what it returns is it also returns an array of like anything. And this is where immediately TypeScript jumps in and says, hey, the argument of type string is not assignable to an array. And that's because it doesn't have properties like push. So we can swap this back to A and B. It will still complain, but once we convert this back into an array, this works. No more complaints. If we now try to execute this though, obviously that doesn't work because we switch from valid JavaScript to valid TypeScript. And this means we need to actually use the TypeScript compiler to compile this now. I showed you the TypeScript compiler, if locally installed, lies in this path. I personally hate typing that, so if you have npm, that is newer than 5.1, you can use npx to just write npx tsc, which will execute the same file. And if we call this with basics.ts now, we will then have a basics.js file that we can execute, and we get 15405. Let's quickly look at how the source code looks like when it's generated. Pretty much no difference. It's the same code that I wrote. The only difference is that it actually dropped all the type annotations, which makes sense because that's not valid JavaScript, so it had to drop these. Cool. Now, as in so many companies, one of your colleagues, the one that kind of loved the fact that they could pass in strings, figures, hey, I would love to be able to actually continue passing strings in there because it worked for me. So we can do that by creating so-called union types. So we basically say, hey, either this input is an array, or it is a string. We don't really care because the function works for both. And this is pretty much what this says. We can also factor this out and say, hey, we're gonna create a new fictional type called concatenable that is either an array or a string, and then assign that here, and that works as well. The source code is still the same that is generated. There's no difference there. But we can take this one further, and we can say that, hey, let's make a function that can really take in as input A a concatenable as well. And here we get two problems. One is that push doesn't exist on strings, and then the other one is that we can't cast a string to an array because input A might be a string. We can actually change this and say that we want to return a string in the end. And this is now where the quick excursion from earlier comes into play. So what we can do is we can use the Typeof operator in here and say, hey, is input A actually a string? And if so, all we do is we return input A plus input B to string. So we'll basically just merge these two strings. And then this also immediately drops the error message for push. And the reason is that TypeScript did a so-called flow analysis. So TypeScript understood that, hey, if this condition is given, input A clearly must be a string inside here, while here it was still a concatenable. So inside here it must be a string, since there's a return statement. Therefore, input A later must be an array. And now we see the last error message is, hey, I can't cast an array to a string, so there's something off there as well. We can just fix that by saying join, comma, and now we wrote a function that is able to take both strings and arrays and is still safely typed, so we can make sure that nothing else can be thrown in there and that we handle all the scenarios. Cool, so far I've only written some basic ES5 code here, and I told you that basically everything new at JavaScript is supported as well, so we're going to jump over to write another file that I call dbts, and inside here we are going to create a class called database to show a couple of other examples. And inside this database, all we're going to do is we're going to have an internal DB, which is just an object where we're going to store all of our information. And then we have a set function that gets a key and a value, which is a number. And then we just set the internal database to be that value. And similarly, we need a get function which gets a key of string and returns a number. And all we do here is return this internal DB key. All right. So if we try to initialize this and try to access it, we immediately see, all right, so we have get available, we have set available, but we also have access to the internal DB. That's something that's common in JavaScript because there are no private properties in JavaScript yet. But it's not really what we want people to access, right? That's why we wrote a get and a set function. If we could just use that, it kind of drops the whole purpose. So TypeScript actually has, since version 1, a property called a statement called private that we can add to properties and methods that make these private. So if I now hit you'll see I only have get and set. And the important thing here to remember is that this is not fully private. This is actually just private during compile time. So we won't be able to access this during, so we won't be able to rely on this during runtime. Similarly to the type checks that are being dropped during after compile time, while the runtime checks like typeof, for example, stay. So if we set something like foo and give it a value of 42, we can then say foo is db get foo, and this code works. So if we compile this, npx tsc dbts, let's test if this works. All right, so the code works. Let's take a look at how it actually looks like. So first of all, this was how, that was not the latest version. So this is how the latest, this was supposed to be basics. So this is how the latest code of the basics work, right? It dropped all the TypeScript specific things, but it kept the JavaScript specific things like the typeof check, for example. If we go into the db.js now, we'll see that it changed the code quite a bit. And what it did is it actually, by default, TypeScript will down transpile your code to ES5. So since we've been using classes, it basically down transpiled it to a function using prototype. And it started using var instead of const. So inside of that, there is not much change, right? And it dropped the checks for the values. All right, this looks good. I mean, we're using type check, so we should be good, right? This is totally type safe now. But unfortunately, it's not, because I can show you, for example, if I change the signature to Boolean, this will still work. This will compile, this will run, there's no problem. And the reason is that TypeScript has no idea what's in the internal DB. So while we can see like, all right, so internal DB is private and client kind of sets the values and gets the values, so there must be like only numbers in there. TypeScript can't go that far because you might be doing something during runtime or like during compile time, somewhere in a different part where you're accessing this. So as a result, and the reason is that internal DB is typed as just an object without any additional information. So what we want to do is we want to type this internal DB with more information. We could create another type, but what we're going to do is we're going to create an interface. And the difference between a type and an interface is effectively that interfaces can, for example, extend classes. They can be extended from other interfaces, and they can be redeclared multiple times. So you can, for example, have across your project multiple times that you extend the interface with additional information. Inside here, we could write something like foo is a number, and then we can specify here this, and we'll get a compile time error. And the reason is that property foo is missing on this when we initialize it, because we don't specify it. We could turn this into an optional, and the compiling error goes away, but what you're seeing is we can still do this, and this should actually trigger a compile time error. The appropriate thing we actually want to say, though, is we want to say that, hey, this object stores a bunch of different keys that are of string that map to numbers. And now you see that we suddenly get this error that number is not assignable to Boolean, which we were hoping for in the first place. So we can switch this back to number, and we have a way safer code now, because from now on, wherever we try to access this.internalDB inside our class, we know that it maps strings to numbers, and there's no way we can like get something else than numbers. Now, this is not really like this is pretty much set in stone, right? We want to make this a bit more flexible, and this is where, in the world of types, generics come into place. So generics are fictional types where we say, hey, this dictionary has some fictional internal type T that instead of storing keys that are strings to numbers, we really want to store strings to this fictional type T. And then we just need to specify here, we actually want to store numbers, and this works now, and we can reuse this dictionary interface across the code base for different things whenever we want to store something in a dictionary. We can take this one further and make the whole database, for example, generic, and say that instead we're storing T, and we adjust that everywhere here. So now if we hover over database, it will say that right now, because we didn't specify a type, it's storing any object in there. And if we set it, we take any object, and if we get it, we get any object returned. But as soon as we change this to number in here, suddenly the signature says that, hey, it requires as a second parameter a number, and this one returns a number. Similarly, if we change this to string, suddenly we have a compile error here that says that, hey, 42 isn't a string. So we have a way more flexible interface now. Cool. So far, like we can compile this again, but there's not going to be any difference here. So if we compile this and look at the JavaScript file, there's no difference here, and the reason is that interfaces, just like types and anything TypeScript specific, gets dropped. Like it just disappears. So we don't have to worry about that. All the code that we've been writing so far didn't rely on any external code, right? If you've written code before, you probably used some external module or some other third-party library that someone has written. And the chances are high that these haven't been written in TypeScript. So how can you use these and still write like safe code? This is where so-called definition files come into place. So you can imagine definition files as files that only contain things like interfaces, type definitions, or empty classes. And basically, based on this information, TypeScript then knows how to actually treat something. So let's say we want to import, since this is Node code, we want to import the event emitter from the events module, which is a built-in Node module, so that shouldn't be a problem. TypeScript uses the native ECMAScript module syntax, and we're getting the complaint that it can't find the events module. And the reason is that so far we didn't tell TypeScript that we are writing Node code. This might as well just run in a browser where there is no events module. So how can we change this? This is where we need to install one of these definition files, specifically the one for the Node environment. Until TypeScript 2.0, this was sort of complex because there were different tools. Now it's as easy as running npm install and use the @types organization and then specify the module that you're looking for, or in this case, the Node environment. And if we install this and save this, and then reload this, not this file, that file, the error went away because suddenly the events module exists. In fact, we can go and look at it. And this is how a definition file looks like. So you're seeing a bunch of different functions here. This is, in our case, for example, the event emitter. It specifies all the methods that we have and stuff, but there's no implementation here, right? This is all just plain old types. So in fact, if you would compile this file, it would equal it to nothing. Because there's no valid JavaScript in there. Cool. So now that we have that, we can go ahead and use extends here and actually extend from the event emitter. And this means that now we have a bunch of additional options here. So we can use an add listener, emit, basically everything that TypeScript, that the event emitter class has as methods. And we also get type information about this. So we can use emit, which expects a string or symbol. So in our case, we're just going to call it update. And then we can pass a bunch of arguments. We're just going to pass one, which is going to be an object that has key and value in there. And this is really cool because suddenly you don't have to dive for every module that you're using. You don't have to dive into the documentation to figure out what were the arguments again that it retrieves, or like kind of trying it yourself. TypeScript will just tell you if there's a definition file for it. And similarly, now we can use this on the instances, so we can listen here on update and say key value console log set key to value. And if we compile this again, execute it, the code works. So let's take a quick peek again at the generated file, and you'll see, I told you earlier that there's not, like, TypeScript doesn't typically add stuff, except for these kind of cases where it has to down transpose something like the extends, so that it can do prototypal inheritance. So it basically added this blurb here. There is a way, if you do extends in a lot of situations, there's a way now to kind of like factor that out, so that you only have it in one file and you don't have it like 300 times across 300 files. But basically that's the only blurb that it kind of added to it. Similarly, if you would kind of down transpile async await, for example, it would add a couple of additional boilerplate code there as well, so that it can use async await. But aside of that, there's not much additional code that was added here. It added this one because I was using destructuring here, so this code changed into option available right now, commented, so that we can turn the ones on that we're interested in. So for example, ES5, as I said, that's the default option. It's currently available, and we can use the out dir here, and we can specify out. So this will basically put all the files that we're trying to compile, run the compiler again. What this will do is it will not only grab every TypeScript file it finds along the way, it will also grab every JavaScript file along the way and run this through the compiler as well. So if we look at it, we now have an index.js file here, which not only has been moved into the file, it also has been down transpiled to ES5. So we could change this to ESNext. For example, run the compiler again, and you'll see it uses const again. And so, yeah, we'll keep this. The other option that you see underneath it is check.js. So this is really cool because we can now gradually move from your existing JavaScript files and move them slowly into the TypeScript universe. So the first thing you might want to do is turn on allow.js just to kind of have everything in one place. The next step would be, hey, how type safe all my JavaScript files by itself? So you could do that by going either into your index.js file, and if you want to do it on a file-by-file basis, you can add the @tscheck argument, which will then start using the knowledge that the TypeScript compiler has to start checking if the things that you're doing in that file make sense. Similarly, you could later go and turn the check.js flag on and instead say like, hey, this file, I know it's broken, so I'm going to ignore it for now, but all the other ones should run through the compiler. And you find amazingly interesting stuff here that might be bugs that you wouldn't have realized before. So for example, if you have a document.query selector that by default returns potentially a null as well, which are you checking every time you're using query selector for null? You might not in some cases. TypeScript will tell you that. So this is something that is super useful. And once you feel confident, you can just go ahead and actually rename your JavaScript file to .ts and just go on from there. The other question that I typically get is how you can use TypeScript how you can write node modules in type file. But if you want to gradually move over, no implicit any and no implicit this are nice because they sort of force you later to always type everything rather than implicating that this might be anything. And then obviously we're handling compiled code, so source maps are useful as well. To wrap this up, in summary, a couple of things I want you to keep in mind. The first one is you are already writing TypeScript because every valid JavaScript is valid TypeScript. The only benefit that you really get from TypeScript is that it might actually find bugs in your code that you didn't even think of or never tested. So it's really helpful there because it allows you to ultimately write safer code since it has this deep understanding. And since there is this deep understanding, it also gives you a better development experience. You can do things like refactoring. You know, no more like search and replace. You just say like, hey, I want to refactor this method, change the name, and it changes it everywhere across your code base. Or now they introduced a feature where you can say like, hey, these 5 lines of code, factor them out into a new function, and it will generate you a new function and replace it in the correct area because it has this deep understanding. If you wanted to kind of go again through like how you can integrate TypeScript into an existing project, I wrote a blog post about that a while ago, but it's still up to date. And I put the slides up to this URL. I'll tweet about that after the talk, so you can check it out there as well. With that, thanks everyone for your attention. Again, my name is Dominik. I'll be hanging out afterwards in the break in that room. And then later there will be a roundtable about TypeScript as well if you have any questions. So thanks for your attention.